Hello everyone, welcome back. My name is Mr. Kovold, and in this video I'm going to show you how you would calculate the molarity of one solution after finding the pH of another solution. So let's get into this. Okay, so in this problem we're asked to calculate the pH of a 0.0010 molar solution of HB, a hypothetical acid with a Ka equal to 9.6 times 10 to the negative 5. What molarity of acetic acid would have the same pH as this HB solution? Now HB is usually a generic way of identifying some generic weak base, right? So HB would be the base. If you said HA, that would be a generic acid. So here we're looking at a hypothetical acid called HB. Sometimes it's HA. So you know it's a hypothetical because you got B. That wouldn't be boron. But anyway, I digress. So let's do this problem. So here, the first thing we need to do is do an ice table to find the pH of the hypothetical acid. So they gave us the molarity to start with. What we need to figure out is what the equilibrium concentrations are going to be. So let's go ahead and write out our equation. So the equation of HB reacting in water, right? We're going to have H2O. That's going to be in equilibrium with the hydronium ion, H3O plus what's left over is your B minus, the anion, whatever that is. And then they gave us the Ka for this substance, which is 9.6 times 10 to the negative 5. Okay, so let's do our ice table. So the initial concentration we're told is 0.0010. So we'll put the head here for HB, 0.0010. Of course, we don't care about water because that's a liquid. That's not going to be part of our equilibrium expression. And we start with 0 amount of H plus and 0 amount of the B minus. Okay, so then since we got 0 amount of products, it's going to shift in this direction to make product. So that means we're going to lose an X amount here. We're going to gain an X amount for hydrogen and B minus. And then we add those together, we get 0.0010 minus X, and then we're going to get an X here and X there. So now we can write our expression for Ka. So the Ka expression for this is going to be, again, concentration of products. So concentration of the hydronium ion multiplied by concentration of the anion, again raised to the powers of their coefficients. The coefficients are 1, so they're powers of 1 here, and then we're going to divide that by the concentration of HB. Again, we're ignoring water because water is a liquid, and liquids and solids do not go into the expression for the equilibrium constant. So here we're just going to put in the concentration of HB. And then we plug in our expressions for the equilibrium concentrations in terms of X. So we're going to have H3O plus and B minus on top. So they're both X. So X times X over, and then HB concentration, which is 0.0010 minus X. So we'll put that down here, 0.0010 minus X. And again, that's going to be equal to 9.6 times 10 to the negative 5. Now all we have to do is solve for X. Now here, we're going to do the X is small approximation, but if you look at the Ka value, which is a negative 5, has 10 to the negative 5, and we look at our initial concentration of HB, which is 1 times 10 to the negative 3, -3, -5. This is really close to 1 times 10 to the -4. So 1 times 10 to the -4 here, 1 times 10 to the -3 here. That's about a factor of 10. That's highly unlikely that this assumption of x being negligible will hold. But let's go ahead and look just to verify that's the case, but that's what I think. So if we do the x is small or x is negligible assumption and we get rid of x, we'll multiply both sides by 0.010, right? So we multiply this by 0.0010, and then we'll multiply this by 0.0010. So that's going to cancel out. Oops, I didn't mean to cancel that out. That's not going to cancel out. So that's going to be 0.0010. And so when we multiply this together, right, we're going to get, let's see, we're going to get x squared. So this is x times x squared. And then when we multiply this together, we're going to get 1 times 10 to the -3 multiplied by this. So we're going to end up with 9.6 times 10 to the -8. And then if we take the square root of this, we get x is equal to 3.098 times 10 to the -4. And so let's check this assumption. Let's go ahead and calculate the percent ionization of this, or the percent change here. And we do that by taking the x, the amount that we formed here, the amount that was dissociated or ionized. That's going to be 0.8 times 10 to the -4, and we're going to divide that by the initial concentration, 0.010, 0.010, my bad, 0.0010, and then we're going to multiply by 100, and when we do that, we get 30.98%. So this is equal to 30.98%. So in order for the x is small here, that assumption, in order for that assumption to be valid, our percent error here, our percent ionization, the percent here has to be less than 5%. And obviously that's not less than 5%. 30 is much greater than 5%. So that indicates that this assumption is not going to hold. So in this case, what we can do is do the method of successive approximations. And the way that works is all we do is we take our x value here and we plug it in for x and we solve for x again. And we keep doing that until we get the same number repeated in succession. Once we get the repetition, then we know we've reached our x value. So let's go ahead and do that. So I'm going to erase this, and we're going to basically use this equation over and over again. So I'm going to erase this to give myself some space, right? So let's go ahead and rewrite it over here. So we're going to use 9.6 times 10 to the -5. That's going to be equal to x squared over 0.0010 minus x. So all we're going to do is take this x value that we just got. This will be considered x sub 1. and then this is going to be considered x sub 2, so the next iteration. So we're going to take this value, we're going to plug it into here, 9.6 times 10 to the negative 5 equals x squared over 0.0010 minus, and then 3.098 times 10 to the negative 5. Let me put a line here. And so now all I have to do is subtract these two. So I get 9.6 times 10 to the negative 5 is equal to x squared over, what did I get? 6.9 times 10 to the 4. So again, you get 9.6 times 10 to the negative 5. Okay. Oh, sorry about that. That's going to be 6.9 times 10 to the negative 4. So we get 6.9 times 10 to the negative 4. And then all I have to do is I'm gonna multiply both sides by the bottom here, isolate x squared, and then take the square root. And then when I get, that's going to be x sub 2, the second iteration of x, and what I get is 2.573. So 2.573 times 10 to the negative 4. Yes, negative 4. Okay, and so you'll notice that here I have 3.098 times 10 to the negative 4. Here I have 2.573 times 10 to the negative 4. So this second iteration is not the same as the first. So I have to do it again. Remember, the process, the point of the successive approximation is to keep doing the iterations of this until you get your x value repeated. Now, since we got two sig figs here, and we have two sig figs here, we really just need to repeat it up to 2 sig figs, 3 to be on the safe side, right? So typically you'll just keep 1 extra sig fig. So we want repetition up to the 7 here, right? So 1, 2, 3. These first 3, we're looking for repetition there. As soon as we get repetition there, then we know we're done with the successive method of successive approximation. Now, you might be worried that this is going to take a long time, and especially if you're on a quiz or a test trying to use the successive approximation. Just keep in mind that all you're doing is taking the value you got for x, and notice here, all you're going to do is you're going to subtract from the initial concentration, then multiply by Ka, and then take the square root, and then repeat. So subtract from the initial concentration, multiply by the Ka, take the square root, subtract it from the initial concentration, multiply the Ka, then take the square root. If you get used to that, you can do it pretty quickly on your calculator. And I have a video that also in which I go over how to do that pretty quickly. So check that video out. But you can get pretty quick with this, so don't worry. Once you get the hang of it, it goes pretty fast. So this is x, the second iteration. Let's do this again. So for the third iteration, let me go ahead and erase this so I can repeat. So I'm going to take 9.6 times 10 to the negative 5 is equal to x squared over 0.0010 minus x. So I'm going to plug this into here. I'm going to repeat the process, and then that's going to be my x to the third, my third iteration. And when I do that, I get 2.6700 times 10 to the negative 4. So you can see here that the x2 value here is not the same as the third iteration, but they're getting closer. The difference is getting closer. So let's keep going. So now I'm going to take 9.6 times 10 to the negative 5 equal to x squared over 0.0010 minus x. So again, I'm going to plug this into here, subtract from the initial concentration, multiply by the Ka, take the square root, and then the fourth iteration I get is going to be 2.6526. 2.6526 times 10 to the negative 4. So notice now I get the first and second digits are repeating, but I want the third one to repeat. Remember, I want to keep an extra significant figure, so that way we're avoiding any error there. So we want to go one more digit. So now let's do it another time. So once I do that, right, so I'll set it up again. So we have, again, x squared is equal to, oops, sorry, not x squared, sorry. It's going to be 9.6 times 10 to the negative 5 is equal to x squared over 0.0010 minus x. I take that x, plug it in, subtract, multiply, and then take the square root, and I get x to the 5th. And for that one, I get 2.6558. 2.6558 times 10 to the negative 4. And now, look, I have the 2, the 6, the 5 here, and here I have 2, 6, 5. And so on. And then, if I needed 3 sig figs, I would keep an extra one, and then keep doing it until I repeated the 2, 6, 5, 5, right? But since we only needed 2 sig figs, and I kept an extra one just to be on the safe side, it looks like we repeated those 3, so we are done. So now I can take this value and use for x. And so at this point, it's not an approximation anymore. This is the actual value based on using the method of successive approximations. And so now I can take that x value and I can use that as the concentration of H3O plus, since that is related to x. So to get the pH, all I do is take the negative log. So pH is equal to the negative log of 2.6558 times 10 to the negative 4. And when I take that, I get a pH that is equal to 3.575. 3.575, which is also rounded to 3 sig figs, or in this case 2 decimal places, since we took the log. So remember, we're only allowed 2 sig figs here, right? And when you take the log of something, those 2 sig figs translate into decimal places. So for the rule for logs and sig figs is that whatever number of sig figs you have in the measurement that you're taking the log of, that translates into that same number of decimal places. So since I have 2 sig figs here, that translates into 2 decimal places here. So I have to keep 2 decimal places. So the 5 is dropped, the 7 is rounded to 8. So I get 3.58 for the pH. Now for the second question. So now that I got the pH, they're asking me what molarity of acetic acid would I have to have in order to have the same pH as this hypothetical acid. Well, I set up the ice table again, but this time, since I know the H plus concentration that gives me this pH, then I work backwards in my ice table from the known concentration of H plus to giving me whatever the initial concentration must be for my acetic acid. So let's go ahead and set that up. So here we'll keep the equation here. And we will keep this, since we need that, erase this. And so here we'll write the acetic acid equation reacting with water. So we'll have acetic acid HC2H3, H3O2 plus H2O in equilibrium with H3O plus acetic acid acetate ion, which is going to be C2H3O2 minus. Okay, again, water, we're going to ignore water. So in this case, we know H plus concentration to begin with. So at equilibrium, since we want the pH to be the same, that means that the concentration, the H plus concentration must be the same. So we're going to put in our 2.655 times 10 to the negative 4 for the H plus concentration. I dropped the 8 because, I mean, we only need the extra 1, so I kept 2. So again, 1 or 2 is good for avoiding any rounding error. So now remember, when this ionizes in water, the H3O plus concentration is going to be equal to the anion concentration. That's just the way this works for your monoprotic acid. So since this is a monoprotic acid, it's going to ionize, and you end up with the exact same concentration of H plus or H3O plus and the anion. So we'll write that down here as well. So this is going to be 2.655 times 10 to the negative 4 concentration. And so this is going to be the concentration, the initial concentration. We'll call that initial concentration. We'll call that, I don't know, concentration of A. And so here, so if the initial concentration was concentration A, and then we lost an X amount of A, then that means that the equilibrium concentration of the acetic acid is going to be A minus X. Okay, so water we don't care about, we're ignoring water. Okay, and so here, if we're losing X here, then of course we're going to gain an X amount here, but that gain of amount of X is 2.655 times 10 to the negative 4. And again, we're going to gain the same amount here, so 2.655 times 10 to the negative 4. We started off initially with 0 amount, right? So 0 plus this gives us this. So we have the change. Remember, X is the change. And so that tells us that this here, X, is a negative. It's a subtracting 2.655 times 10 to the negative 4, which means that this X is also going to be 2.655 times 10 to the negative 4. And so now all we have to do is, now we have the equilibrium concentrations here. Now all we have to do is plug it into our equilibrium expression and solve for A instead of X, right? So same thing, but now we're solving for a different thing, where instead of solving for X, we're solving for the initial concentration. So let's go ahead and set that up. And so here, the Ka expression for acetic acid is going to be, again, the concentration of H3O plus times the concentration of the acetate ion, C2H3O2 minus, divided by the concentration of acetic acid, C2H3O2. Now we're going to plug in our values here. So this is going to be equal to, since these are the same and they're multiplied, that's going to be squared. So 2.655 times 10 to the negative 4 squared, I could write that better, squared divided by, and we're going to have A minus 2.655 times 10 to the negative 4. And then that's going to be equal to the Ka value for acetic acid. And that's something you could look up in a table. So if we look that up, we get 1.8 times 10 to the negative 5. So this is equal to 1.8 times 10 to the negative 5. And so all we have to do is solve for A, right? So if we solve this, we're going to multiply both sides by this, right? So this will cancel out. So let's go ahead and write that down here. So 2.655 times 10 to the negative 4, that's going to be squared over A minus 2.655 times 10 to the negative 4 equal to 1.8. Oops. Sorry about that. Okay, so we have 1.8 times 10 to the negative 5. So now we're going to multiply both sides by the bottom part. So we're going to multiply by A minus 2.655 times 10 to the negative 4. So, and then we're going to multiply that by on this side. So A minus 2.655 times 10 to the negative 4. So that cancels out. And then we would distribute this to both sides. So this ends up being 2.655 times 10 to the negative 4 squared is going to be equal to this times A. So we get A times 1.8 times 10 to the negative 5 minus, and then we multiply 1.8 times 10 to the negative 5 times 2.655 times 10 to the negative 4, and we get 4.799 times 10 to the negative 9. Let me double check that. 4.77, no, oops, 4.779. 4.779 times 10 to the negative 9. And then all we're going to do is add 4.779 times 10 to the negative 9 to both sides. So we're going to add 4.779 times 10 to the negative 9. So we add that. We're going to take the square of that, add that number, and then we'll have, and then we divide by that. So we're going to then divide by that, and then we should get, finally, A is equal to 4.2. So A is equal to 4 point, what did I get? 184. 184 times 10 to the negative 3. Round to 2 decimal places, or 2 sig figs. So then the A is going to be equal to 4.2 times 10 to the negative 3. So that was the initial, that would be the initial concentration of the acetic acid that would give us the same pH as the pH of HB solution that we calculated for the first part. So I hope this is helpful. I hope this I hope this helped you out a lot. If you found this interesting, if you found this video helpful, then please by all means like the video, share the video, hit that like button. Also make sure that you subscribe to my channel, help me out. Hit that notification bell up there so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think, ask me questions. I would love to hear from you. Thanks for joining me and have a great day.